Hello there, children. Today, we're going to work in section 4.2, Radians and Degrees. This educational experience is brought to you by your rad dude of Radians and Degrees. That'd be this guy, Mr. Faust. So we're going to talk about radians and degrees. You've definitely heard of this one before, but you might not have heard of this one. But before we get into that, time to take care of some definitions for some things. Alright, the first definition we need to cover is what's called standard position. The vertex of an angle is in standard position at the origin, and the initial side coincides with the positive x-axis. Now, what in the world does that mean? That means if we have a coordinate axis like this, standard position, something simply means one side is on the positive x-axis right here. The origin is the point of the vertex, and the point of the angle comes off somewhere. Doesn't have to be exactly like that. Could be down over here, over there, up there, but as long as the vertex point is at the origin and one side of your ray is the positive x-axis. Now, a positive angles are generally rotated by counterclockwise rotation. So they're generated by counterclockwise rotation. So those of you that actually forget what a clock is, one of the ones with the hands on it, counterclockwise rotation goes like this. Counterclockwise. So this would denote, right here, if I drew an arrow like that, that would denote counterclockwise or positive rotation. Conversely, negative angles are generated by clockwise rotation, which would be like this. So here, to generate a negative angle on this original problem, I simply go around like that. That would generate a negative angle. Think opening up for positive, going and flipping downward for negatives. Now, some more definitions. Note, one thing we need to talk about, Greek letters are often used to label angles, as well as uppercase letters A, B, and C, instead of lowercase. Now, you've seen theta before to measure an angle. Alpha and beta are also used when you already have theta included in a problem. So a lot of your problems, if you're trying to find two angles, they generally use theta for one of them, and then they'd probably use alpha or beta for the other one. That's very important. And A, B, and C capitals can also be used for angles. Lowercase would be for sides. Coterminal. Coterminal means angles have the same initial and terminal side. So all that says, if you could have something, two angles, like the ones here, they're the same angle, except one of them I rotate around this way, and one of them I rotate up. If they start and end at the same spot, they're coterminal. That's how you can remember it. Doesn't matter how many times you spin it around. If they start and end at the same spot, they are coterminal. A central angle, one whose vertex is the center of a circle. So if I got myself a circle here, and I put an angle right in the middle of it, that would be a central angle because it's in the center of a circle. Not exactly reinventing the wheel there. And just as a friendly reminder, in case you forgot, a degree, a second way to measure angles in terms of degrees. So we have a way to measure angles. It's denoted by that little degree symbol. And in case we forgot, 1 degree is 1/360th of a rotation of a circle, which is why, by the way, circles have 360 degrees. Now, why are we talking about this? Because of the following. Now, the other way we are going to measure angles in here, get ready kids, it's radians. Oh yeah, radians time. That's the other mode your calculator has. We always talked about you got to be in degree and radian mode, and I've been saying Wait for radians, they're coming. Dun dun dun, here they are. So, what are they? Now, we have the following definition. What is a radian? A unit of angle measure with the following definition. So, here we go. 1 degree equals pi, pi is coming into play, over 180 rad, or radians. Now, where does this come from? Well, radians is kind of a shorthand for radius, and it was first used, this particular terminology, by Roger Coates in the 17th century. He didn't call it radians back then, but he pretty much thought all of this stuff up. Now, where did they get this idea from? They looked at a circle, and here's a diagram for you. So, folks, if you look here, here is our circle. Now, if you notice here, half of our revolution of a circle makes pi. A full revolution of the circle makes 2 pi, which if you think of a circumference of a circle being 2 pi, it kind of makes sense. That's why that formula has 2 pi in it. So, this is what we have going on here. The circle goes around pi, and then 2 pi, which is going to make our conversion factors we are going to use very, very intuitive. So let's go over the conversion factors. So the conversion factors are as follows. How do we convert these wonderful things? Okay, we need to be able to go back and forth between degrees and radians. Now I know what you're saying to yourself. Why? That's the excellent question. Why do we need to go back and forth? Well, some formulas back in the day were loaded with degrees or radians in mind. Some formulas work better with degrees. Some formulas work better with radians. So we have to figure out which one is which. So to go from degrees to radians, we need to be able to do the following. The conversion factor you are going to use is pi over 180. Why in the world am I using that? Well, let's think about that for a second. If you look back at our definition for radians, radians included pi, so the pi has to be up top. Pi over 180, because if you remember, 180 degrees, by our little diagram there, is pi radians. That's why I am dividing by the 180 and introducing the pi. Conversely, to go the other direction, to go from radians to degrees, I need to take the reciprocal of that. So from radians to degrees, I need to have 180 over pi. Now in the terms of angle measures, 180 is the same as pi. So I'm really just multiplying something by 1. I'm just adjusting it by a conversion factor here. Now, to go from radians to degrees, radians oftentimes include pi. So the pi needs to be in the denominator to cancel it out. And I need to multiply 1 by 180 to create a larger number. So for example, 45 degrees. How do I convert that to radians? And how do I convert 2 pi over 3 radians, and that's what you will see, to degrees? Well, in this case, I multiply by the factor of pi over 180. And this one, I want to do the reverse, which is 180 over pi. Easy way to remember these, folks. The physical number that you see should grow when you go from radians to degrees, and it should shrink when going from degrees to radians. This will be pi over 4, because what you end up getting is 45 pi over 180, and 45 divided by 180 is simply Just 1 over 4. We don't want the rho in. We also do not multiply the pi in. Leave it there. It'll be very important for our computational purposes later. And 2 pi over 3 is the following wonderful measure. That is 120 degrees. Now you are ready to do the homework. Oh, happy days are here again. Go henceforth and do. Woo! Enjoy.